and hopefully you guys feel better. But yeah, we got introduction to functions. Okay. Now, this section of all the sections usually is a good indicator of how old I am because I start using more ancient type things. You'll see. But just real quick, okay, below is a formal definition of a function. I'm not going to read that garbage because it's so academic, it's so nerdy that I almost feel like you guys would beat me up if I read it, okay? So, not that you should beat up nerds, by the way, but I'm not going to read it because I don't give a crap about it, okay? All this is saying is that for your x values that you have, you can't have more than one y value with your x value. That's it. Okay, now the second part though, that's important though. The domain is the list of the x values, and it's a list, right? So that I think that goes back to 2.1, and I know you guys have been waiting for this. It's come back for the domain. Sometimes you got to use these fancy brackets, right? And to close it, right? Again, it'd be like a 2, then an S. Man, that's so pretty. Well, the output are all the y values, okay? So, well, you're just going to list them. Now, it'll ask for interval notations on these as well, but most of the situations that we're going to see are, they can be written as inequalities as well, but sometimes it's just like 1 or 2 values. So, yeah, maybe I'm misremembering. Maybe we won't need those fancy brackets. I was just so excited to see them. But again, a function. Let's go into this just a little bit deeper. If you like to be a nerd, then okay, congratulations to you. I'm a nerd too. I'm a math nerd. So, back in the day, they used to show us these in what they called function machines, and yeah, they'd put a little window in that thing, and they'd say, this is a conveyor belt, and then stuff goes inside the machine right here, right? That's called the input. They used to have computer games about these machines, which was not nearly as fun as the actual machines. But again, these are the x values, okay? And I think we've had at least a little experience with equations, 2 variable equations. If not, that's fine. Now, the x is going to run through this machine, right? It's going to go all through this machine, and it goes through the window, of course, because it's more interesting that way. And then when it comes out, that's called the output. And that's our y values. All right, now, a machine functions, or what the heck just happened? I don't know what happened there. Well, if you put something in a machine, hopefully it's, something's coming out. Now, it may look different on the other side. But if it starts putting out different things, right? Like let's say this was like a microwave, you know what I'm saying? And you put in some kind of mystery box, okay? And then it spits out a burrito. Oh yeah, that'd be real good. Like, you like a burrito, I like one too. And it's like, wow, that's so great. But then you get a mystery box, it looks exactly the same, and you put it in the machine, but then it spits out a pizza. Now you're happy that you got a pizza, but it's like, man, I really expected a burrito, I'm still going to eat the pizza. I feel like maybe this is worse than it is better, but it needs to spit out the same thing every time. Like, if you put in this mystery box, you need a burrito to come out in order for this machine to be functioning. If it starts spitting out pizzas and candy bars and ice cream, you're still happy, but it's like, man, it's really malfunctioning, right? It's not functioning. So we need the x values to spit out the same y values in order for this to be considered a function. Now, in 1010, they'll expand on it, and they say, well, your y values have to spit out the same x values. Okay, but that's a whole different matter. So if we look at a problem like this one, okay? Now, remember, in these are ordered pairs, right? Let's look at the ordered pair. And it looks like an interval notation, but it's not. It's saying that you got an x value here on the left, and then you got a y value here on the right. So for this one that we have, just to start out with, right, we got a 9 right there. That's a negative 9. That's our x value, and then its corresponding y value is 9. Okay, so that means whatever this machine is, you're going to stick a negative 9 in, and then it's going to spit out a positive 9. Well, the next time you come to the machine, you put in a negative 9, and it's like, dude, I can't wait to get this 9 out of this thing. I'm going to eat it all up. But then it spits out an 8. It's like, what the crap is going on? In fact, the next 2 times you put in a negative 9, it spits out even different things. And it's like, dude, this machine it's malfunctioning. So if this was, I know it didn't ask you guys, I kind of feel like I got ahead on this one, but it's definitely not a function. It's not a function because you're putting in stuff and then suddenly different things are coming out, right? It's kind of like a gumball machine. If you put in a quarter, is it $1 these days? But if you put in money and then it spits out like 3 gumballs, it's like, whoa, that was pretty sweet. But then if it spits out 2 gumballs the next time, you'd be really disappointed. I mean, you're still happy to get the gum, but you'd realize that machine is now malfunctioning. So this one's not a function, but it did say to list out the domain and range. So I'll start with domain. And remember, the domain is all the x values. And since we're just listing one value in this case, we do need the fancy brackets. They're so pretty. Well, what x values do I have? I have negative 9, and then I have negative 9, then I have negative 9, and negative 9. It just repeats, so we don't actually have to show all of the negative 9s on that, okay? In fact, whenever you guys see values repeat in the domain or range, you don't need to list it more than just the one time. So that's the domain. R for range, and yeah, I'll keep it kind of consistent with the colors on this one. Well, what y values did we see? We saw 9, and 8, and 7, and 6, right? That's back up here, 9, 8, 7, 6. And even though I listed those from greatest to least, it doesn't have to be in any specific order. Even the homework, the computer program in the homework would understand if you would list these out of order, or if you went like least to greatest. It doesn't matter. All right, so this one is saying which of the following sets represent valid functions. So again, if you put in an x value, you need to know what you're going to get out on the y values, right? So here's a negative 4 and negative 1 right there. Well, there's no other indication to show that I put in a negative 4 and get something different, right? What about 1? Yep, there's no other 1s, there's no other 5s, 7s, or 16s to contradict what we have in this set, right? Remember, it's got to put out something different, but there's nothing in this set that shows it would be something different. So yeah, this one is a valid function. This one is, that's set R. Well, what about set S? Well, let's find out. Well, here's a negative 1 input, and then it spits out a 0 output, right? Well, as it turns out, there's this other input of negative 1, but then it spit out a negative 2. That means that this machine is malfunctioning, at least for the negative 1. So that's not a function. It's no good. Well, what about this next one? Well, the 0 doesn't show anything else, so the negative 4 is fine. It's just this next one, though, right? Here's a 1 input, and here's another 1 input, but it spit out a 3 and then a 6. That's malfunctioning. So yeah, we're going to cross this one out. Not a function. And then finally, this last one, it doesn't show any contradictory x values that could be contradictory. Now you may look at the negative 4 here and then the positive 4 and say, well, they're putting out different outputs. Yeah, but they're different inputs. A negative 4 is not the same as a 4 input. So this one, again, there's nothing to show that it's malfunctioning. So this one also is a function. That's set F. Now keep in mind though, okay, and I don't want to throw a wrench in your explanation, because it is correct, okay? It's just like, let's say that, let's look at set S. Yeah, I'm going to get rid of this stuff after all. Let's say that, right, set S, it had the negative 1, 0, and then the negative 1, 2. If the 2 was a 0 right there, it's still producing the same result, right? The input is still producing the same output. And in that case, we would have said that it would have been a function. All right, so for this one, we're going to figure out the domain and range, right? And remember, the domain is all of the x values. So I'm just looking at these first values in these ordered pairs like this. And we can see, right, and yeah, when we list the domain, we need our fancy brackets, but I got a -2 right there, so I'm going to put it in there. Now, as it turns out, all the other x values are also -2, so I don't actually need to list any more of those. Just showing one -2 is enough to say that the domain on this is just -2. So the range is all of the y values, right? So let's highlight these so we can see them. So we got 4 different range values, 4 different y values. We got 6, 5, 4, and then finally 3, right? So we close it with our fancy brackets, and this lists the domain and range. Now, this last part says determine whether the relation is a function. And to do that, right, well, let's go back, right? Up here it shows that -2 will spit out a 6. Right here, -2 is spitting out 5. Here, -2 spits out 4. That's no good, you guys. Even this last one, this -2 spits out a 3. Since it's spitting out different values, this one is not a function, okay? So whenever you see x values that spit out different y values, even if it's just one different y value, then it's automatically not a function. So domain of root functions, since even roots can have negative radicands, don't worry about that, for roots of expressions, again, that's pretty nerdy. What we're saying is that if you ever see a square root like this, whatever's on the inside, it can, like if it was x right there, it's coming up. But that value has to be, it can be equal to 0, that's true, but it can't ever be negative. You can't have square roots of negatives because then you're dealing with non-real imaginary type numbers, and they do exist. All you're going to do is you're going to take the inside of that radicand, it's just a square root, you guys. Fancy word for it though. Right, you're going to say the domain is this. It's whatever I solve from this as long as it's greater than or equal to 0. Always greater than or equal to 0 with square roots like this. Well, to solve it, right, you'd say I'm going to subtract 9 from both sides. Now I get -x is greater than or equal to -9. And yes, some of you guys see we're going to divide both sides by that negative phantom 1, which does still flip the inequality. So as long as x were less than or equal to +9, then it would give us any kind of value. Rational or irrational, doesn't really matter. But at least it produces a real number out of this. Okay, right? Like 9 minus 9 is 0. But as soon as I go less than 9, then we're in good shape. Like even if x was a big negative number, it ends up being 9 plus whatever that negative is, because a minus a negative produces a plus sign for us. So that right there is the domain, but it wants it in interval notation, right? So, you could say, well, I'm going to look on the graph for it, and I kind of feel pressed for time, but I'm still going to show it, okay? Right, you'd have a closed circle at 9. It's not eating the x, so it goes to the left, which means the domain includes everything to the left of 9, all the way to -infinity, going to the right to 9, which is included, so we put a square bracket on that. If you deal with fractions, you never have to worry about your numerators. All you're going to do is look at the denominator, whether it's x minus 8 or 18 or 18.1, it doesn't matter. It can even be 3x. All you want to do is show that the denominator cannot be 0, because if it's 0, you start dividing by 0, you start getting some really weird things going on because it's infinity. So like this one, right? Again, there's a numerator, but I don't care about the numerator. You're just going to focus on the denominator, you guys. So I'm going to say, well, that's x minus 4. It just can't equal 0. I can't have a denominator that is 0. So what value of x would make it 0? Well, just add 4 to both sides like you would as though this were a regular equation. And we see that x cannot equal 4. Now that is the inequality for this. If it asked for the interval, right, we'd have to show an interval that includes all the numbers except 4. Well, that means it goes from -infinity all the way to 4, not included, but we'll restart the line starting at 4, not included, going all the way to infinity. And yeah, it just may ask for the interval notation. So one like this, right, the domain. The domain, again, I don't care that the numerator is a 1. I wouldn't even care if there's an x in the numerator. All I'm going to say is that x plus 3, it definitely cannot equal 0. And by the way, if you guys like the slash to go this way, it doesn't matter. I'm left-handed, so my slash goes this way. So we'll subtract 3 from both sides of this, and we'll say x cannot equal negative 3. As long as x isn't negative 3, we're in good shape. But again, going back to that interval notation stuff, how do I exclude negative 3 from the entire number line? Well, it has to go from negative infinity all the way to negative 3, which is not included, so we got regular parentheses there. And then we'll unite it, again, just starting again at negative 3, but it goes now all the way to infinity, and that would be the interval. It's going to be a little bit more complicated than this garbage, right? Thank you. And then, and even the numerator, you'll even, I lost it. Yeah, so when you guys take Math 1010, what you'll see is that there are x values in the numerator, and sometimes they can even cancel out some of these x's in the denominator, but because we started with an x in the denominator, it never really mattered. We still have to figure this out, values of x that would make the original equation imaginary or undefined or infinity, okay? So on this one, even if, like going back to the original question, do we always not care about the numerator? When we're looking at the domain, yes. Don't have to look at the numerator, don't have to even think about it, no matter if it's an x to the power of 2, if it's got fractions, decimals, integers, doesn't matter, just ignore it. Yeah, that's a great question. So functions, like on this one right here, functions are just a different way to write an equation. Now, a function has to indicate that any x value is only going to produce one y value, and that is true when we use what we call function notation like this, okay? So in the past, where you guys may have seen slope-intercept form, which it's very common, though it's not used very often, y equals mx plus b, that would be the regular equation form, but really what this is it's a function, so you may see it written as f of x equals mx plus b, which is, again, it's just the function notation. So if I haven't said this before, math people use a lot of different words to describe the same things, and that's why people think we're really, really smart, even though we're not, but we just confuse people with our vocabulary. So to answer that question, yeah, it's almost like a confusion factor to an extent, although there is some technicalities. Now on this one, just on a smaller note, y would be, again, this is very technical, and some of you guys may use it, whether you're taking like science classes or seems like they use this in political science as well. But in any case, you got dependent variables and independent variables, okay? X is, that's the input, that's independent, and y is dependent. You'll never be quizzed on that stuff. But it may be helpful in the future, so just know that you heard it here first, I guess. Now right here, let's go back up here, right? This reads f of x. F of x, it's a function of x. It's just a short way to say function of x. So right here even I'd say f of x equals mx plus b. That's because this function is relying on the x. It's depending on the x, which goes back to the dependent variable thing. Now when we see something like this, f of negative 12, it just means that x is negative 12. That's it. So just like before, where we may have seen an expression like this, like x to the power of 2 plus 3. You guys remember that? And then it said, well, x equals negative 12. Well, what did you do? You replaced the x with negative 12, then you solved, right? Not negative, yeah, negative 12, right? Replace it with negative 12, 144 plus 3, 147. That would have been the answer for that. This is the same thing, it's just that the answer would be written as f of negative 12 equals whatever you get out of the expression after evaluating it. So let's look at some examples. I think that should clarify some of this stuff. All right, so on this one, f of x, again, that reads f of x equals 9x plus 2, but this says f of 3, right? So, writing this out, let's see if this pull up. Twice. F of 3 equals 9x plus 2. But again, it's not x, it's now 3. So I replace the x with 3, and then I just solve it. Now, the formal way to write this out would be f of 3 equals whatever this is. And 9, right, order of operations, 9 times 3 is 27, plus the 2, bam, it's just going to give us 29 on that. And so this is kind of the full answer. I mean, in the homework, you'd just type in the 29, but if you were writing this by hand, you'd have to write the f of 3 equals the 29. Now, this is leading into something different as well. This is going into the graphing stuff, which we talked about 950 in Module 7. This becomes an ordered pair for us. It's 329 as an ordered pair. And while I don't need to cover that in too much detail right now, because we're not actually graphing this, but if you wanted to, you could say, well, this function has given me my ordered pair, and it feels so good inside. Now we got the 6x to the power of 2. I'll write this in. 6x to the power of 2. So I'm going to put some parentheses there. I'll fill them in with whatever x value tells me to. And starting with f of 0, right? So I replace these with 0, 0 to the power of 2. By the way, we're using calculators, so you could just type this in with the parentheses as you see it. In fact, what the heck, I'll use my calculator. Where did she go? So yeah, the calculator gives us -4. Now going back, right, it's f of 0 equals -4, which would then show us what the ordered pair is on that, okay? Now I kept this on purpose so I could just erase this garbage so that I could now do f of 2. So I replaced the zeros with 2's on this. And if you guys had used the x storage button, you could have just done it, but I didn't, so whatever. 6 parentheses 2 to the power of 2 plus parentheses 2 minus 4 equals 22. So f of 2 equals 22. Yeah, we use the calculator for that. I recommend using the calculator. It's a very good resource.